So why this conformational space is very much important in our computer-aided drug design is clash-free space. What is clash-free space? The atoms are not in self-collision. Say we are having Lipinski rule of 5 less than 500 molecular weight. There are so many atoms are present in that particular rule. These atoms should not have a collision with each other. That is intramolecular collisions. Obviously, we are going to have intermolecular collisions when the ligand is attached with the protein. But before that, we are going to see the intramolecular collisions. For that, we are doing a conformational analysis to the conformational space. So these are all the search method we have already seen previously. Now we will do one by one. So this is the one which we have got already number of conformation we can calculate by the 360 divided by the delta. That is rotation of the increment in the degrees, that it can be either 30, 60 or 90 or 10. And n bonds, that is a normal letter n bonds, that is a number of rotatable bonds. We have already mentioned when you are having this number of rotatable bonds more than 6, you are going to have a exponentially high number of conformations we are going to have. That is the reason it will make the complex system. Why? Because if you see here, when you are having a rotatable bonds very high, you will have a combinatorial explosion. Because if you have got a 3 rotatable bonds, for example, you have got a 30-degree increment in your conformational study, conformers generated are 1728. And it takes around 29 minutes, around 30 minutes to study this particular pattern with a 30 minutes increment. If you want to go further to 20 or 10, it will increase further and conformations will also be more. Say, for example, if you want to go with 5 rotatable bonds, and same 30 degrees increment in your conformational study. So the total number of conformers are 248,832. So it takes around 69 hours if you are going 5 rotatable bonds to get the conformations of all these states. So time for 7 rotatable bonds, if you want to see, that is more than 6, it will take 415 days. It means more than a year. So more than a year it will take to find the conformations. That is the reason it is very complex when you want to see the conformations of all them. That is depending upon the number of rotatable bonds, and you want to have how many degrees of increment you want to make it. So degrees of increment you want to make it with lesser one. Then it will be more that you are studying all possible predictions. When you are incrementing with orthogonal nature, opposite directions, if you want to go, then you will have a less number of increments. But the problem is you are going to lose some optimal positive conformations. So that is the reason we need to take a compromise between this time and your degrees of increment. When we have got a rotatable bond fixed in our moiety in the ligand, because we have already seen previously pharmacomapping and ligand optimization that rotatable bonds are required for us, so we cannot change them. So explore the large regions with the high energy, that is very much important in the energy minimization. So it is not good for highly flexible molecules because they will have flexibility, they behave as they like. And it is very good for rigid molecules so that number of conformations will be very less in them. So therefore, it is a time consuming and cannot be used for the large system where we have got a ligand complex in nature. That is the one which we need to see. The second one is search tree. In the search tree, what will happen? It will eliminate the time consuming energy minimization stage for the structure that have the very high, large, and you will be having a rotatable bonds are very high. In those cases, you will make a tree. In the tree, you are having a root node, and each node will be having a branches 1, 2, 3, and sub branches you are going to 4, and further you are having a multiple atoms in the sub branch, and you are going to have a intramolecular collisions. So in the collisions, what you are going to do in this conformers with severe intramolecular collisions, you will put the cutoff or interatomic van der Waal contact energy greater than 10 kilocalories are removed by default. So when you are fixing this as a bar, that is 10 kilocalories per mole. So when you are removing it, your number of confirmations will be less and the time will be reduced by the search tree. So you are searching within the molecule and taking each branch and further going down and putting whatever the confirmations which are having greater than the van der Waal forces 10 kilocalorie per mole, those we are going to remove it because they are the high energy states. We don't consider them for this conformational search so that our load will be less. This is what the third method, what we are going to use as a major input. Another one is the molecular dynamics methods. We are going to have a model building with respect to each fractions of your molecule. In this particular case, you construct conformations of the molecule by joining together three-dimensional structure of the molecular fragments. So previously, what was the problem? In the search tree, we have made the bar, we have kept it as a bar. Say, for example, in ideally state, some kilocalories are bound to be required present with the steric factors involved in the molecule, where we are going to ignore those critical one, but we are going to lose there. That is the reason we are going to use the molecular building approach. In the molecular building approach, so the construct the conformations molecule by joining together the three-dimensional structures of the molecular fragments. So these molecular fragments, what we are going to take, so we take the molecule and individually split these fragments and we find out the high energy zones and we map them. So substructure algorithm is present. In the substructure based algorithm is present. In the substructure searching, it is finding the mapping for the query to target molecule. In other words, no bonds are broken and no new bonds are formed, and we are going to see the fragments. And where we are finding, getting the clarity, then we are going to take a decision to make the conformation of that particular fragment with respect to the molecule, which is going to meet our requirement in nearby future, take a decision. This is what the molecular building method. So we have got a systematic approach that is deterministic, and we have got the second approach, Monte-Carlo simulation, that is a random and stochastic methods. So where we are having the confirmations number, when it is you are thinking that very high, then we are using a bar by fixing the bar of a 10 calories. Then we are going to reduce our confirmations with search tree methodology. Then if you don't want to lose each structure impact onto the final molecule size, then we see the fragment individually and find its impact and see the confirmation. But conformational, we are where we are going to take that confirmation in a particular direction or angle that we are going to fix for the substructure search algorithm and model it. This is actually what the confirmation analysis we are going to do. So what are the softwares are present in this particular case? Because everywhere, every topic we have got tools and softwares. And this is required to be present a few one as a memory Bloom taxonomy level 1. You have to memorize, there is no other option. But when you are using them with our own hand in the practice, then what will happen? We will be able to remember it with very ease. That is the reason I have given one assignment to you. I hope you have already written that. When you are coming back on Monday, you are going to submit that assignment. So this is going to give you some acquaintance and make you comfortable with Bloom taxonomy level 1, where you are writing with your own hand all the software and tools and databases with your hand with the purpose and what you are going to write at the end, what you like. So that way, that part, it will help us to memorize this. And these are all the software packages which are available to do the conformational analysis. Again, I will take attendance part, just a minute. If students are there, good. So CAT confirm and confirm, that is from Accelerates, that is a part of Discovery Studio pharmacophore modeling protocols. Tool provides the two different search modes. So that is a fast systematic search and the distance geometry, where we are changing the bond lengths based on one atom, individual atoms. So these two approaches are present with confirm and the CAT confirm. So the program system like CORINA and rotate. So these are all the web-based available in the molecular networks. So where we can see the fragment impacts with each. There is another version is called as Omega, OMEGA, from OpenAI Scientific Software. It is a fast systematic. What the systematics deterministic search we have done in the first approach. So knowledge-based method, it can be used. Macro model from the Schrodinger is well known and widely used for the force field analysis and molecular modeling package, offer the variety of method for the confirmation generation, where we are going to do the energy minimization and molecular modeling and water effect removals also with each. This is an advanced paid software. We can get all the options starting with energy minimization and conformational analysis and molecular docking and get the scores directly. Comfort was developed by the Professor Perelman, University of Texas, Austin. He has distributed by the Tripos. The Comfort performs the exhaustive conformational analysis of a molecule. So this can be help. There are other open source software for the academics, freeware, that is called as a Open Babel or RDKit. So they are provided the means to generate the set of the molecular conformations. So these shapes we are going to do docking again later, so that we will have a final score, so which is the better. This is the way we can manage our moiety, which is going to have a better conformation that is going to work in the pocket, that is a pocket of the receptor, that is our so-called protein, which is related to our disease treatment with the ligand. It means these are very good important for the fragment-based drug design and ligand-based drug design, where the structure of our protein is not known. So still we can take the drug which is already functional and present in the market. We take them and we will provide the bioisospheres and we get the similar shapes without making a same lead. We can generate the new lead, so we can enter into the market. In this journey, we may get another receptors are also get bound. It will open new market also to treat the new diseases. This is how this CAD is emerging to treat the untreated diseases and to improve the disease treatment with the existing molecules and finding a another parallel means for finding its side effects, like so-called toxic effects, and get the parallel effect for the new indications also. It can be helpful, because why it is a new indications? If you are taking a old drug molecule, putting in a different sockets, that is where the receptors are present. If they are giving a good affinity scores, it means that they can also work there. And we are going to find out their toxic effects or the beneficial effect. Accordingly, we can proceed further. With this, we will have our course completed and we will see. So 25 number are present.